Yes, welcome to this episode. This is Engineer Juma Kim. Um, this is just simple question. Maybe some of you may have also asked yourself about the same. I normally ask myself for this current generation, um, how were programming in the old days done? Part programming may have been tedious to some extent because machining is a process. Um, Looking at the complexity of the part, how are they considering time when they are machining? How were they considering um, quality? How are they considering cost? And when you look at programming, I have seen most of the machines were using what you call the NC, numerical control, which may be using punch tapes, things like punch tapes. So it may have been a challenge, but now technology has come into play. How does it help? So I have just crafted this simple question. Maybe it will help somebody. If you look at the struggle of manual machining or manual programming, there are many things that these people should have considered when they were programming. But yes, it was tedious. If you happen to have used this machine, you need to be competent. Yes, you need to be competent enough to use this machine because the quality you will achieve will determine on how competent you are. So if you ask yourself, what were the challenges? You can list down some of the challenges. Maybe you are first using conventional machines or NC machine, numerical control machines that were using punch tapes to do programming. And because now technology has changed, every day we are asking ourselves questions. Machines are becoming complex. So what now solves the programming? So that's why this has been crafted to answer those questions. If you look at these old days, manual programming, they will sit down, they calculate cutting parameters. They will calculate all features required to do a programming, which means it was a lot of taking a lot of time, tedious. You at the end of the day, you are tired. And if you are machining a complex feature, it will take you a lot of time. You also need to calculate cutting parameters, making what you call manual script from the drawing. You're given a drawing, then you do a blueprint of it. That is the manuscript blueprint for G code, so that you can write down the program and then transfer using punch tape to the machine. You can call it punch tape. So this one will require somebody to be experienced. So if you look at how these people are doing, this is what you call manual script. They are writing down the manual script before transferring the machine. It was tedious, yes. So the person writes the program, it transfers the machine using punch tapes here, then you start program. You start now machining. So if you ask yourself questions, maybe if you are born during that time, will you have made it? And now, are you making it? As technology has changed, are you making it? What were the struggle of manual programming? Ask yourself. Were you meeting the quality desired? If you look at the World War I and World War II, many countries were struggling because of quality. That's why technology came into play. So programming was tedious. Struggling, calculating the diameter. Yeah, you check the diameter. because you need to write all points down if you're using point-to-point programming or continuous programming. And then you need to understand the operations, maybe facing, chamfering, face turning, external turning, corner radius turning, taper turning. All of these parameters you need to calculate the angle, maybe the curvature, if you're using R or CR or CV. So it depends how it was. Yes, those machines you may have taken a lot of time, since at the end of the day, at some point there might be error in your program, and this error will cost you a lot in terms of maybe the material being affected, the part being affected, or even the cost increasing. If you look at time factor, programming something which was complex, it may take a lot of time. Like, let's look at cavities. You are looking at programming cavities. You are looking at programming core, like molds, blow molds, and ejection molds. How are they taking it? There were also delays in terms of programming, since it is done manual. You're using a manual script to write G codes down, then you transfer using a punch tape to the machine. So you look at these challenges, then you ask yourself, was it worth it? Now you are born in this era. You have struggled, maybe your generation was struggling with programming during those days, and now maybe they are there, they have seen how technology has changed. And in today's era, how will they cope with technology? If you look at the past, and we look at how transition has come into play, and we look at the present, you can ask many questions. In the past, when you're programming, most of the workshops were heavy loaded. Machines were, so many of them were so huge. People will sit down at a table, calculating those parameters, putting it on the punch tape, then they set the workpiece or it can be cut. But technology came into play. Using computers, we have computer-aided integrated manufacturing softwares, like what you call CAM, computer-aided manufacturing softwares, that has come into play. And in the modern world now, workshops, we have SolidCAM. We want to go to SolidCAM. We want to see how this SolidCAM will help us understand the time factor of programming part in for CNC turning. We want to look at how SolidCAM works vis-a-vis the manual way of programming, because this SolidCAM is now the current technology they are used in industries for production purposes, industrial design and production purposes, to help you create 3D models at the same time, program, generate toolpaths, do a simulation, then generate G code. So the main objective now here, we want to compare the traditional way of programming and today's way of programming using technology. And we are going to look at SolidCAM. We want to design in SolidWorks. Then we create toolpaths. After creating toolpaths, we do a simulation. From the simulation, we generate a G code. Then we see how efficient it is, how time factor it is. So welcome and follow our training. Then we will also compare the length of the program vis-a-vis the length of the program during those days, how it was. So let's go dive into SolidCAM. Yes, let's dive into SolidCAM. This is our SolidCAM. Yes, we want to understand how you can program this SolidCAM. We cut this part, and then we look at the challenges today using software and the challenges during those days using manual way of programming. Welcome. I've already done my part. Maybe I'll show you the sketch. This is a simple sketch I want to assume I want to machine. These are some of the parts. The diameter I was showing you is here, illustrated well. So these are the radius one. If you multiply by 2, you get the diameter, but these are the length. So we want to, I don't want to calculate, the software does itself because I'm using technology. I don't want to calculate the radius, I don't want to calculate the chamfer or whatever. I want to use the way it is because this software has done simple work for me. So let's follow step by step on how to create a part program using SolidCAM. In this, I'm using alloy steel. My material is alloy steel and have one part. So I'm using SolidCAM 2021. Maybe you can use other versions, still it will work. So first step is ensure you have SolidCAM. If you're using SolidWorks with the embedded SolidCAM or adding SolidCAM, you go to your options here, above here, then your add-ins. And add-ins, you see all of the add-ins here. But now I'm using SolidCAM version that is integrated with CAD. So already this one is added advantage for me because it's only for computer-aided manufacturing. So let's start one by one. You can go to SolidCAM here, and then create a new part, send turning. Then you can click maybe save. I didn't save. Okay, you click save. It opens up as simple as that. Then let's go hand in handy to see how this will work in SolidCAM. So how SolidCAM eliminates the need for manual part programming. This is simplest way how SolidCAM works. So you start from SolidCAM operations, click new, turning, then click here. You can use external part saving or you can save project as internal. Then you click OK. Let's move. We want to see how this one will work. Okay, you can pick your machine, you select your machine here. Because mine, I'm using Okumal, I can use Okumal. Or if yours is DMU, you can use DMU. Depending on your machine, you can pick the machine that suits, that you have. The type of the controller or the type of the machine you have for your purpose of programming. I'm using Okumal. Then pick on coded system. First thing is to set up. During all days, they were doing also setup, but how do we set? Because you need to set the part origin where the tool will start cutting. So simple setup here, you click on coordinate system, that is the part origin, where you use either G54, G2, G59, using the ISO part programming machines. Then here you click on center of the revolving phase or revolution phase. Then you can pick any of this phase. It will put you the coordinate system here. The coordinate system must be, the Z is blue, should be pointing away. Then the X should be pointing either up or depending on the tool approach, if you're using up, or up, down. So it depends on how your tool orientation is from your machine. So mine is moving from up and down. So I'm along X-axis for facing and along Z-axis for turning. I use face turning or cylindrical turning. Once you finish, just click OK here. Then next, here just click OK. You can go to, we want to look at how this one works. Because I'm only using one part origin. I don't need to put another one. I can just click OK. Okay. You leave it to do what you call parsing. It scans the part, the model, and then it generates a profile or a rectangle profile along the Z-axis or along the Z path. Then you can, this one, the target, it has already picked the target. Maybe I can expand it more. The coordinate system is where the part origin is. The stock is the material that is not cut. Then the target is the material that is cut. So the material is not cut, it should be more above this region. So the material is, the target is this part. So the material which is not cut should be above this region here. So let's go to stock. We want to define our stock. Simplest way to do this one is SolidCAM. You can use absolute coordinates here. Then you can say take the stock dimension. It calculates stock dimension, so you're able to know that here on the Z positive, that is the Z positive. I want to do facing, I can put 2 mm for facing. You see now the stock, the green color is the stock material. It increases. The material which has not been cut, then Z, I can say I have minus, for holding purposes, you can add 20, I have minus 110 or 100, it's still okay for this. If you're using a material which is hollow, you can put here internal diameter, but mine, the stock will be solid, so I did not put internal dimensions here. Then the diameter here, because I cannot cut this part well unless the material for the external diameter should be more. So if the workpiece is 70, then it should be maybe 75. You can have a 75 stock. Then I click OK. So this way I've created my stock. So this, the green, the blue, black color now, it has changed to black color. From the green, which was displaying as a stock, now the black color region is a half of the of our stock, which is half of the material. Then here, because I only have one part, the target is all selected, so I did not pick again, click OK, then I proceed. The next step is, for this SolidCAM, you need to create your holding place, the jaws. Where are you holding the jaws? So you come here to set up, then you click on, you right click on setup, then you say edit. We want to position our stock. Then under edit here, click on this one, table clamping. You see it generates this one, this color. I don't know, is it purple? It generates a purple color. This is the jaws. The jaws, where are you going to hold it? So I'm going to hold the other side, because the jaws are inside. I want to position it far away. So and then I click on the tool positioning. Then I click here, pick Z. Then I pick a place somewhere here. Then I click OK. I can say now minus maybe 105. Then I click OK. The value here will become positive, but the other side, if you pick, it will become negative. So you can put a negative value here. Now you see my jaws has moved from this point to this point, so that when a tool is it will be approaching, it will not crash into the jaws. It will be away from the jaws. Okay, you can put a negative value, or you can click anywhere, then you position it. Here it becomes negative, but when you leave it here, it becomes positive. That's okay. Then you click OK. Next is, now we want to add our operations. Take time, we see how fast we'll be using this one to program, and then we compare with the traditional way of programming. Then come here to operations now, right click, because we have done our setup, part origin, putting the stock dimensions, putting where our chuck will be, and then now we go to operations. So the key operations here, which are very simple, we have facing operations, which will be done here. We have straight turning, fillet, chamfer, combine. So this is a combination turning. We go to turning operations here, then click face. Do you want to do facing? On facing, click this new. The geometry is where you want to cut. Where do I want to cut? So you click on new geometry, and then you can pick on this line. It should move down. It should move down. If you look at it, it should move down, and then you click OK. This line, the one I've picked, this whole line. So this line should move down. So maybe I can click, I can close again, come new. Then you pick this line for facing, this line here. It points down. You see there's arrow pointing down here. Then you click OK. Then you click OK again. And then come to tools. So the tool you want to use for cutting. You remember here we are now using G18. G18 is X, Z plane. Now the red one is X, the blue one is Z. So the tool is approaching from X. So we go to tools, then click select. Here we want to add external turning tool. So scroll down, come here, external turning tool, double click on it. It will open up. Then you give the profile. I'm using DNMG 1504. Use capital letters, DNMG 150408, and then press 0408. Then it updates itself here. So this is the tool I'm going to use, and then I click on this part, this one, to remove the positioning, so that I allow it to position the tool here, so I can show it well here to see the positioning of my tool. The tool has been well positioned. Once I've done that, I go to cutting parameters. The holder is this here, cutting parameters. I can adjust my cutting parameters, 500. The finishing can say 600. This one can be 600 also. You can use cutting parameter which is fitted per millimeter or per revolution. This is G94, this is G90. This is G95, this is G94. If you use G94, you can put 100. If I use G95, you can use 0.1. So these are the cutting parameters. When they were calculating, they need to put these parameters when they are cutting using manual programming. So once you do that one, you can also change the holder, the cutting point. You can also pick the holder. You click on this tool to change the location. You can click on this one to change on the holder size. Maybe you're using square. It is straight tool. Here it is MD. So you put MD, MD, J. Then here the size was 15. Again, you put MD, J, and R. That is MD, J, and R because my insert is DNMG. So the holder will be MD, J, and R depending on what you have. Then the size is 20 by 20. I'm using 20 by 20 like this. Then the K, I'm using K15, so I can change here to K, meaning the size of the length of the holder. That is K. Once I'm okay here, I click, I accept here the challenges. Then I go to level, safety, I can put like 3 away. I go to technology. Here I can put equal, put stairs. Then you can put this one or to leave the material or not. Then go to links, click calculate. Then let's go to do a simulation. You click yes. You do a simulation, yes. Then you click on turning. This one turning. You can click on turning. Then you click simulate. So it shows us how it is cutting. That is what we call simulation. So when you're using software, it's easy to cut. And remember here, this material it has left because I left those materials. How do you remove it? So we can put here maybe 0, 0. Then we calculate again. Then we do another simulation. We see here how it cuts. We can use turning, click on turning. Then you click here to play so that you can play. Then here it shows the cutting parameters when it's approaching. This is the cutting parameters when it's approaching. Now it has removed the material. You see it has removed. This is what you call facing. You are now doing facing. Just cutting on a flat surface, call it facing. Also in milling, you have what you call face milling because you're cutting on a flat surface. So here you can also do, you can click exit after we finish, or right click here, then you say you have what you call, you have, you can generate a G code, or you have this SolidCAM simulation also. It has its own simulation, so you can do SolidCAM simulation. You can do that one, then you click play, it will do the simulation, as simple as that. Yes, so we want to go and add the last operation. Right click here. This one shows the toolpath. So these are the toolpaths now. How are they calculated toolpaths? The software has done it. It has done compositions. I'll show you why. Come here, operations, turning, then do turning. I want to use the same tool for rough turning and face turning. So click on this one, and then the profile, I can start from 0, zoom this region. Where am I starting from? I can start from maybe here, because that one I have finished. Then go pick the last one. I can pick the last one here, like this. Let it calculate until the last end. Then once it finishes, click OK. Then tick here. Yes, I'm using the same tool. Pick the same tool again. Come here. I'm using the same tool here, tool number 1, for doing turning and finishing. So I'll show you how to do semi-finish. Then come to levels, put a level of 3 away. Then here, you are doing rough turning, removing material first, but leaving some material on the surface. Then come here to rough technology. How much am I leaving? Maybe 0.2. And then you come here to semi-finish. I want to use the same tool for finishing. So click here, ISO turning. Then ensure that you put here 0. Then click here compensate to compensate. So the tool will compensate itself automatically. So I don't need to recalculate again. The tool will do it itself. Then strategy here, you can pick the descending motions or non-descending. So I'm using descending motions. Break materials, you can leave the way it is. Then here you click calculate. Once you finish, you see the tool parts have come here. These are what you call the tool parts. The blue one are the cutting one. The red one is the tool approach. The tool moves away when it's cutting. Let me do a simulation. We see how it does. So click this one icon. Do a click on then say simulate. Let's go to turning. You can minimize this. Maybe if you want to see it well. Sorry. You can minimize this one. You can use your mouse to minimize this. You can position it at the center well, like this. Maybe to see it. You can increase the speed here. You can click on this to show the color, different colors. Maybe this one the colors. Here the data when it's cutting, it shows you the data when it's cutting. Then here you can say maybe show also the rest material. You can show the rest material. Here it can display the colors. You can change the color that you want to display. Then here you can also stop on the next in case. So I want just now to click here, then show the data, then click here, we play, we do a simulation. Do you see here, the blue one here, it is my jaws. So the jaws are far away. So the tool will not knock in the material. Then you see the blue one line, these blue lines, they are the cutting lines. They are now using what you call G01. I will generate the G code, I will show the G code, you see how it look like. Then the red ones here are what you call the tool approach. The tool moves away from the workpiece. This is the target, this is what I want. I want to achieve something like this. And then here, you see this color, it is leaving a material on the surface. So which means it knows that that material is compensated for finishing, left for finishing. So once it does rough turning, it will come again to do finishing on this material. Let's watch, let's see how SolidCAM has what you call revolutionized the computer integrated manufacturing, or CAM, from the old ways of programming to the new ways of programming. Welcome, and let's watch as we finish. We wind up this, we generate a G code, then we compare how tedious was it me using SolidCAM and how tedious was they using manual way programming during the 1950s, 1960s, and even 1970s. Yes, so let's finish this. We see how technology has changed or has shaped the industry of CNC programming. It is almost finishing, almost finishing. I don't want to go fast. I just want to move the step so we achieve our target. Yes. We want to achieve our objective for this case. You'll see it will come and do finishing. Now that is the finishing it's doing. It knew there was material that was left. Now it's doing what you call finishing. And the work is perfect. It has finished. It has moved away. The red ones, as I said, is tool retraction. The blue ones here are the tool cutting or approach. So this is what you call the tool parts. How are these people calculating tool parts during those old days? And how is software helping us to calculate tool parts in these generations? And how is it helping to automate the industry of CNC programming and CNC machining? Okay, we have finished. So let's go and generate a G code. We want to generate a G code. It is very fast. You click on this one. I want to combine. Press the control down, then select these two, then right click on it, then say G code generate. G code generate. Then right here maybe maybe G2 one. Okay, any word. You can write any word. Okay. Let's see the program. Let's see the program, how it look like. So this is what you call, this is the G code. You see it has generated G code. Yes. Maybe let me zoom a little bit. Let me zoom a little bit. This is what you call the G code. I wrote G2, so this is the name. I can put here the when I'm editing, I'll put here the semicolon. This one it will jump. I can check my program. This one I'm using old system. I can use the old system and put maybe my machine is just normally Fanuc controller, so I can put 0101. Then here I don't want to put the activation of the gears, so I can leave this one. I can change this like this. How I want to see the time we are using to edit the program. Somehow the current one, it now depends on the controller. If you're using Siemens, I will not edit the parameter because of the what you call the post process. But if I'm using other controllers, I need to check the current parameters before I take on the machine. And this one normally takes the least time. You don't need to take a lot of time editing this one. Yes. So this is what you call the G code. I have programmed using SolidCAM. I have generated I have done what you call simulation. I have generated the part, the G code itself. Then I'm able to check the program. So this is the program. The red lines are the approach. The green one and the blue one are the cutting. The green one is using G01 linear cutting. Then the blue one, which is G03, is using circular interpolation in the counterclockwise direction. Then this one I can also change. If I'm not using this, able to change very fast. Can come to maybe to edit this. Can say maybe replace this, all of them. Can replace, copy this. Then you say replace. Then you say use R. Then you say replace all. Then you say yes. This one is very fast when you are editing it, very fast. I have replaced all of them so that when I put on my machine, it will not stuck. I can also change this. In case I want, I can remove this or I can leave the way it is. When I put a semicolon behind it, it will not cut. Then here, if I put M30, the machine will, the program will start, will stop, will finish, then it runs to the start. So this is what we call a G and M code. G meaning preparatory function, and then M meaning miscellaneous function. So we have looked at how software SolidCAM has changed or shaped the industry from the old ways when we are using manual way of programming to this current generation we're using SolidCAM to help us in programming. So welcome and be part of this exciting moment when we learn how we integrate our softwares to help us in programming. So let's look at what is the, if I might ask a simple question, what is the advantage of now these softwares? How now do we compare the old ways of programming and the new ways of programming? Is there any advantage? Is there any step we may use? So this is key. This is key for our case. So I want us to look at simple advantage. Why SolidCAM? Why now SolidCAM? Is SolidCAM the technology we want? There are so many softwares we can use. I'm not marketing SolidCAM. This is just a question I was asking myself. How are these people programming and how it has brought into reality the aspect of programming in this scenario from the numerical way of programming until today. So if we go into our context, we want to understand how programming has shaped the world. So let's go and then we look at our programming. Let's look at our programming. If we come to our presentations, what have we learned from SolidCAM? One, there is when you compare manual programming, time was a factor. It was taking a lot of time. Second, it was prone to error. Then the work may take a lot of time. But we have used SolidCAM to do our programming. One, the G code is fine because the software itself, it compensates the cutting parameters as I showed you. It is just a click operations. There are very few steps when you're using SolidCAM. Also, it has a minimized number of programming because if you are programming a complex work, it may take you days, but this one we have just taken minutes to program. So in terms of business, so we need to understand the advantage of technology, how it has evolved, and how it is improving production efficiency. So if you are in industry, you can opt to use CAM softwares to help you in programming. One of it is SolidCAM. We can also use MasterCAM. You can also use Fusion 360. There are so many CAM softwares depending on what you're producing. If you're using CNC laser, CNC plasma, maybe CNC router, so you need to check on which software suits your work. Also, it also reduces the mistakes that we make during our manual programming, because when you make mistakes, it is the expense of the company. At the end of the day, those errors has been minimized. The output is improved. The quality is improved. In our real life scenarios, where do we apply this technology? In automotive, we are making gears, we are making flanges, we are making shafts. So we can use SolidCAM to program, automate our quality so that we can make complex shapes for our industry. It has changed. Industry has changed. We have now high-tech vehicles. So if you have high-tech vehicles, you also need high-tech softwares, CAM softwares to help you in programming, to help you in achieving quality. Also in aerospace industries, aviation industries, you need to design components which are high tolerance for aircraft. So that's why we are using SolidCAM to program, MasterCAM to program, Fusion 360 to program, and help you in achieving the high quality features for purposes of aviation industry. Even in medical, making parts for implants, making parts that are used in medical industries. So you need SolidCAM. So this is a real world impact that it is achieving. When you look at the World War I and World War II, there were challenges of quality, there were challenges of mismatch. Nowadays, mismatch has been reduced. So we have reduced this. Why SolidCAM? Is the SolidCAM for the future? I'm not marketing SolidCAM, but my topic is about how do we learn from the evolution of manual programming to SolidCAM programming. Also SolidCAM, it is taking the industry. Why? Most of the mold makers are using SolidCAM. Most of industries are using SolidCAM to program. It has also helped us to automate. You see what I've done? We have just simply shown you how to demonstrate designing, programming, and then we automate our G code so that we can simplify or streamline our programming. It can also optimize my machine utilization, very efficient. No errors, time is considered, material is considered, cutting parameters is considered, so there's no loss until you have experience on using this. Also, it is well integrated. So SolidCAM you can integrate in SolidWorks. So you can use SolidCAM in SolidWorks to help you in programming. It can also ensure that there's a seamless flow of work when you are programming. My conclusion, to summarize this. From a journey from manual programming to modern technology. Yes, industry has changed. From hand calculations, as we have seen, calculating cutting parameters, writing down the G codes to what you call manuscript, and then you use punch tab or punch tape to write the program. Now you have what you call digital the present technology, which is digital. We just program, the program I've generated, I can just put on a USB card, I put on a machine. I can send using LAN. I can just use a LAN cable. I can use USB cable, or I can configure direct to the machine. I just put the parameters on the machine, and then I do the setup, and then it cuts. As simple as that. If you're using Siemens controllers, they are advanced. You can just use direct on the machine without even using the CAM softwares. If you look at now innovations, things are changing. There are so many complex features which are coming into play, making blow molds. If you're using a manual programming, you cannot program a manual part to cut a cavity which is so complex, has different shapes. If you look at the traditional industries at today, the shapes has changed. If the shape changes, so be it. The software for programming to help you minimize the error when the complexity has changed. So this is a call for you. Whether you believe, you conceive the idea, you need to deliver. But for you to deliver, you need to inspire, develop yourself, be the influencer, be the empowerer, learn the skills, know how to solve the problems, be creative, and understand how you can use these skills to make things for the real world. So at the end of it, you deliver skills, maybe change somebody's skill, because skill is life and skill is career. You can build somebody's career, you can employ yourself, and you can gain recognitions. Recognition doesn't come by the name. Once recognition comes, money comes in. So believe, conceive, and deliver. Thank you for following. Any question, you can contact us, or you can chat with us on our YouTube channel, Daryl Cleans Technologies, or you can email us. We'll answer your questions. It may be tedious presentation at some point. Don't worry. We learn by taking time. Engineers learn by taking time. Welcome and be part of this generation where industry is shaping the world through SolidCAM.